And we're going to start off with Dr. Dmitry Garmatuk from the ECE department, and then we'll have Dr. Janet Burge from the Computer Science and Software Engineering department come up and talk with you. They're going to talk about some of the interesting things going on in that department and some of the interesting things they're working on, in particular with undergraduate research assistants. So with no further ado, I'm going to turn this over to Dr. Dmitry Garmatuk and let him talk to you about ECE.
Yeah, I think it's working, isn't it? Maybe not. Is it? Yeah, I turn it on. Is it? How does it sound? Okay, I'll try. Whoa, it is definitely working. Guess it sounds like it. All right, so hello, and my name is Dmitry Garmatuk. I'm with the Electrical and Computer Engineering department. And today I will actually start with something different than my slides. I will talk about my own career a little bit and about the 3 lessons that I've learned during the first 5 or so years of my career before I came to Miami. My graduate study was at the University of Nebraska, where I studied radar, and in particular noise radar, which was a program funded by the U.S. Navy for the purposes of creating a sensor that would be virtually undetectable. So that's what we were working on, and when I got my PhD degree from Miami, I came to work to Intel Corporation as a circuit designer making chips. So if you're trying to make a mental connection between the radar and the chips, the processors, for example, that Intel makes, there is none. I can tell you that right away. There is no connection, and that was my first lesson in engineering, is that engineers are supposed to be versatile. When I was working on radar, it was all about electromagnetics and signal propagation and system design, that kind of stuff. When I came to Intel, they were interested in, you could say, somewhat similar things, but of course a completely different area of application, which was processor design, chipset design, motherboard design, that kind of stuff. So you could say that, well, there was some signal propagation in there. There were some channel characterization research project that we did, but the 2 areas are completely non-overlapping, as you can see. So that was, as I said, the first lesson that I've learned, that you've got to be versatile. You cannot just say, oh, there is one little topic out there, the narrow topic that interests me, and I'm probably going to stay with it forever. Chances are what's going to happen is that you're going to study something in college, then a different thing will be talked to you about at the interview, and then when you actually get the job and go to that job, you will be doing something completely different still. So to be versatile, you have to simply have a right state of mind. So for you, what it means, I think, I would definitely recommend just simply trying different things and staying with an open mind. So taking different courses and trying to see what you like. That is not to say that you shouldn't be interested in any particular topics. Obviously, the more interested there is, the better off you'll be. But again, this is just about the mindset. Don't think that there is one thing that you like and then you'll probably end up doing this for the rest of your life. Likely not going to happen. The second lesson was that when I started at Intel, I was surrounded by seasoned engineers. They hired me as a senior design engineer because of my degree, a PhD. And I found myself a little bit out of water, out of depth, you could say, because I was just starting, and everybody in the group was already 3, 4, 5 years working on the projects, knowing a lot more about circuits than I did, because, as I said, I was working on radars 4 or 5 years prior. And one thing that I started doing was I started looking for things that were different from what they were doing. So I was strong in electromagnetics, something that at Intel or other chip design companies that weren't really doing all that much of. Why? Because probably a good time to start going through the slides, try to keep it as non-technical as possible. Essentially, when processors were designed for low speeds in the 80s and the beginning of the 90s, in the mid-90s even, it was almost like trying to push water from one end of that little backyard pool to the other end. Not a hard job to do. So they didn't have to worry about signals and signal shapes as they were propagating from one end of the motherboard to another end of the motherboard. Signals were fairly clean and fairly strong. Like I said, it's not really that difficult to push that water from one end of that pool to another end. When they went to more complicated motherboards with multiple signal lanes going from processors to chipsets to memory to peripherals to the monitor to the graphics card, other things, it was more like trying to push water from one end of a really long Olympic-sized pool to the other one, and it was complicated by the fact that there are many lines in there. So what do? Well, essentially, you look at the signals and you realize that those signals look nothing what they looked like before. Before they were clean, strong signals, clearly defined ones and zeros. For those of you who are going to electrical and computer engineering, it's going to be very important for you to realize the distinction between 1 and a 0. But here you can see that the signals are not really all that well defined. So what do? Well, you turn to electromagnetics. That describes how signals propagate in different structures like motherboards, for example, or channels in the radar, the wireless channels, or wireless channels propagation for your cell phone signals. As much as those projects or those topics seem different to you, they are, interestingly enough, governed by the same equations, same theories of electromagnetics. So that's where I started coming in, so to speak, and quickly became kind of like a resident electromagnetics expert, which suited me very well. I liked that. I liked the fact that I could branch out from the circuits, where I couldn't compete with the people around me, to something that was different and yet, of course, extremely relevant to the company. So that taught me the second lesson, which was the lesson of multidisciplinarity. If you know circuits very well, you'll probably be able to survive in the engineering world. But what's better for you is to know not just circuits, but also electromagnetics, and maybe even some of the other disciplines that you may not even think as very relevant to electrical engineering right now. So what it means for you, my advice to you would be, branch out and take as many courses from perhaps even different departments as possible. If you're in electrical and computer engineering, take MME courses, take fluid mechanics, take thermodynamics, if prerequisites allow you to do so. If you are in MME or in CSE or in chemical engineering, try to take some of the courses from our department. There is one course that I teach, which is ECE 325, Applied Electromagnetics, that has had a historic appeal to students from other specialties. As a matter of fact, mechanical engineering students who have been taking this course have been doing consistently better than electrical engineering students in it. And some of them had said, well, you know, we've been talking about signal propagation along a line in a motherboard, for example, but those equations look stunningly like an equation for an acoustic wave propagating in, say, liquid. And I said, why wouldn't they be? Really, the physics behind all of these different processes is very frequently very similar. That course, for example, does not require many prerequisites. Mechanical engineering students actually automatically get all the prerequisites for it as they follow their own curriculum. So branch out and try to see what else is out there, because you may find yourself in a situation that you don't want to compete with that many people in the company, but then there is one unique aspect about you. There's one course that you've taken that others have not, and that's where you will break out. The third lesson was about the importance of research. Many people think that, oh, they'll graduate and they will get a job and start making money, and they don't usually think much beyond that. And don't get me wrong, this is very important, you know, to get a first job, start earning money. But eventually, for a majority of you, my bet would be that the bug of research will bite, and then you'll find out that, oh, you want to be creating instead of testing, for example. If you get a bachelor's degree and nothing else, then chances are you will end up testing somebody else's work more than anything else. If you want a creative work, if you want to create something, you've got to go on with your graduate studies. You've got to show independent streak. You've got to think about research and what it means for you right now at this stage. Try to find the faculty, try to identify a faculty who's doing research on some topic that might be of interest to you. And try to talk to them, try to see if they may take you on as a graduate or an undergraduate assistant, or offer a senior design project on that topic that you could collaborate with that faculty on. The earlier, usually the better. There is such thing as, for example, an undergraduate research award. That's the money that the university gives to student-faculty teams each semester for them to pursue their research. The money isn't much, but usually when you're just starting, it is enough for you to do something meaningful and maybe even present it at a conference. That's what I would say you should really keep in mind as a focus for the future. Probably not right now, but sometime into the future, you want to start thinking about doing a conference paper with a faculty member, because that will be a huge impact on all of your subsequent careers. So 3 lessons that I've learned, just shared with you. Be versatile, and that's mostly about just the state of mind. Don't lock yourself in to a particular topic. Always be ready to branch out and think about new things. Multidisciplinarity. Try to learn as much as possible. You never know what may come in as your advantage, your edge among your colleagues. So the more courses you take, the better, but of course you don't want to spread too thin, so there is a balancing act involved there too. And the third one, think about research. Think about what you want to be doing, maybe not 3 months from now, but about 10, 15 years from now. Chances are you would want to create rather than test somebody else's work. So if you think that you've got the potential, go for it. How do you tell if you have a potential? There is no other way than to try now, which means, like I said, identify a faculty member, try to work with them, try to see whether you're good at research or not. Many people underestimate themselves that way. I had a student who thought that he was not good at research or didn't want to do research up until pretty much the last year. And then we started doing the research topic and said, oh, it's a completely different thing from what I thought. I love it. So now he's doing research for Raytheon. Actually, I think I have his slide as a kind of like a, whoa, there's too many slides in there before I get to that one. Yeah, there it is. Oh, a little bit garbled there, but yeah. He's a systems engineer at Raytheon Systems out in California. When he started doing his research, he was very determined. He said, okay, so I figured I love it, so where do I go with it? And he decided that he wanted to work for a defense company out in California. You know, some people are like that. They just want to define their goals very narrowly, and he was one of those people. And he actually ended up working as a systems engineer, airborne RF algorithms and analysis, advanced air-to-air systems development center at El Segundo, California. His office actually looks out on the ocean. So one day he sends me an email, says he's out in the desert on the U.S.-Mexico border. They're testing out a new UAV with a new type of a radar that is supposed to be able to take care of the border very well and basically detect everything, not just above ground crossings, but also such things as tunnels, for example, from up in the air. So you don't have to have people there patrolling the border. You can have several UAVs that are flying around, and then they notice something that is not even noticeable to a human eye, but they are able to detect, for example, tunnel building in the ground. I think for the rest of any questions so far, because I'm now going to show you a few examples of the senior design projects that we're doing in our department. If you have any questions about the 3 lessons that I've learned, you're welcome to ask. If not, I'll just click back a few slides and show you some of those exciting things that we're doing. I'm also doing this presentation on behalf of another faculty member of ours who is very active in the area of GPS, the global positioning systems. She's a world-renowned expert in them. So if you have an interest in navigation, positioning, how do you tell where you are, essentially? Very important topic. Saturday night, right? Then you might look into something like this, something like that array of projects that she's doing. One of them is they're flying to Alaska regularly because they've got a big monitoring station of global navigation signals received from the satellites. And that's about as much as I know about that portion of the project. This is a project that we're doing together with her. This is using a radar as a navigation tool. So if, for example, GPS goes out for one reason or another, what do? Well, there's a sensor on board of a UAV, for example, or an aircraft that is usually there, and it's more difficult to take that one out, and it's a radar. So, for example, what you could do is you could fly over the terrain and you can image targets with your radar. What's the difference between imaging targets with the radar versus just simply taking pictures with a camera? Well, the camera, for one thing, is not an all-weather instrument. At night, it's difficult to take pictures. In the foggy conditions, difficult to take pictures. But more importantly, if, for example, you got some kind of a metallic structure, a tank, for example, a truck, concealed by trees or shrubs, if you take a picture, all you're going to see on that picture is going to be trees or shrubs. If you take a radar picture of that same scene, the radar signal is going to penetrate right through the shrubs, right through the leaves and branches and everything, and bounce back the hardest off of the metallic object, which is the truck or a tank. So what you could do is you could just simply say, okay, so I had a GPS up until a certain moment, so I know exactly where I am right now, but starting from that moment, I don't. The GPS is out. But I do have an image of my terrain beneath me. I know that there is a truck down there. So if I move just a little bit, and then I take a new snapshot of that same scene, that truck is going to appear a little bit farther away, which means that I've moved, in reference to it, some distance, which is not, of course, as accurate of a positioning algorithm as a GPS is, for example. I mean, there you've got 5 satellites that are telling you exactly where you are down to, well, some say now, centimeter range. But in absence of a GPS, that might be just enough for you to survive if you're an aircraft pilot, for example. So that's the research that we're doing that is funded by the Air Force right now. And a student who is working on it is currently a doctoral student at AFIT, the Air Force Institute of Technology. He was our student for the undergraduate studies, and then we got him as a master's student because he liked that topic very much. And then when he graduated, he went on to AFIT. So far, very successful. There was one of the projects, I think last year, the GPS bus tracking. They installed all kinds of tracking devices on those red Miami buses and could track them. They developed an application for a smartphone. They could, in real time, see where the buses are located. I don't know if it's currently being released or not, but it was a very successful project, too. This is something that I've done a while ago, but it was a very interesting project in which they collaborated with the equestrian, I guess, department at Miami and installed GPS trackers on horses. So they could track horses' speed, direction, all of that kind of stuff using a GPS. And that was very useful for the equestrian department people for reasons that are unfortunately unknown to me. Oh, this is the ongoing project throughout several years. This has been an autonomous mower, and now it's being converted into an autonomous, that is to say, fully robotic snowplow. They won a second place in the snowplow competition in, I believe, Minneapolis last winter. The thing can pretty much be like a Roomba. You know, familiar with a Roomba, the little vacuum cleaner that somehow figures out where to go and how to clean the room without your interference. That's kind of like a same concept, but on a much larger scale. So it can clean out streets or big lawns. So it can be converted into a lawnmower or into a snowplow. And it's guided completely by a GPS. Matter of fact, that's what they did in 2009, 2010, using this thing as a mower. Butterfield Farms, familiar with those, just outside the town. They did a maze. They cut out a maze with the Red Hawk, and then I guess that would be a corn husk using a GPS. So they just simply programmed the thing and let it run. There was no human operating that mower. It did it completely autonomously, which, think about it, is kind of a scary thought. Maybe not so much. This was a research project that I also supervised last semester. It was about a radar system that we're trying to make into a cognitive radar, which is another kind of a scary thought because radars are supposed to be operated by humans, and this radar is not going to be operated by humans. This is going to be a radar for a robotic system installed, for example, on a UAV or on a robotic ground vehicle, in that there will be no person involved, no driver, no even a remote driver with a joystick. it will be deciding where to go, where it's at, what to look at, completely on its own. So this is going to be an autonomous sensor device. We are starting to make an inroads. The students actually presented a paper at the radar conference, the most prestigious conference on radar in the world last summer, because we were able to distinguish between a few different targets. And when I say we, I actually mean the radar. The radar itself decided whether it's looking at a wall or at a metallic object behind the wall or even a human behind the wall. So that was kind of interesting. The students programmed all the algorithms, and from that point on, it was the radar's decision. We just simply observed the data. And this is not supposed to scare you with the math. Just simply show some of the results, which I don't think I actually have the time to go into, but bottom line, so far it worked. Still giving me trust. And in 2009, they called the systems engineer the best job in America, which is a slide which I made in 2009, apparently. I think it still holds, though. So, yeah, I think that's about it. That's all I had to say in the time.
Good morning. So my talk's going to be a little bit different. I was told to write a talk on my research. So you're going to see the work that I am doing in the computer science and software engineering department. We do a lot of different things going on. We've got work being done in augmented reality, in mobile computing, in large-scale immersive virtual environments, so computer security, so a wide range of things. And so I did learn one thing. I also worked in radar. So before I came to Miami, I was 11 years at Raytheon Company as a software engineer, writing software and firmware to control radar systems. I then spent 1 year at Fidelity Investments, writing expert system software. So I moved over into artificial intelligence at that time. And then while I was in graduate school working on my PhD, I worked at a small artificial intelligence research company, doing a variety of different kinds of AI-oriented programs with things like genetic algorithms and being able to learn belief nets that help you make predictions about battle conditions. So to kind of get into my research, I'm going to start with the story. So it's Easter Sunday, and John and Marcia have decided that they're going to cook a ham for Easter dinner. So Marcia noticed John's in charge of cooking the ham, and she noticed that the first thing he does is he takes this ham and he slices the two ends off the ham before he puts it in the pan and puts it in the oven. And she's like, well, why did you slice the ends off the ham? That just seemed a little bit odd to her. She had not seen that. And he said, well, that's the recipe. It's how my mother makes it. So Marcia happened to be a scientist, so she wasn't just going to take this answer of, oh, that's just how it is. You know, she's like, well, that still doesn't make sense. So she calls up her mother-in-law, John's mother, and says, so I'm curious about this family recipe with, the ham and the ends off. And kind of says, well, that's just what my mother did. So this is, again, something that had been handed down. So Marcia was still not happy with this answer. So fortunately, John's grandmother was still alive, so she calls her up and says, why, John and his mother said that, the family recipe is to slice the ends off the ham before you cook it. Why you do this? And she gets this long pause, and John's grandmother says, I don't cut the ends off the ham. There's no reason to do that. And then Marcia's like, well, but they said it was the family recipe. And then she thinks a little more, and she's like, oh yeah, when John's mother was younger, we had a smaller oven in the house, and we had a smaller pan, and to get the ham to fit, we had to cut the ends off. So that's probably where she saw me doing this. So here's something that was done just out of necessity and convenience, but is somewhat wasteful by making the ham smaller, becomes this sort of hallowed family recipe that gets handed down, and the reason for why this was done has completely gotten lost. So my research is into the reasons why people do things. Because when somebody is designing anything, whether it's a software system or a mechanical device, You're making decisions. You're having to decide, whether it's, what programming language to use or what materials to use, or how big to make something. You have to make these decisions about why you're doing it. And often this information is lost. So this is known as design rationale. So it's essentially, here's the fairly elaborate definition, but you're looking at the decisions that somebody had to make while designing, and not just what they did, but all the things they considered, and then all of the reasons behind these decisions. So you can sort of view this as you're getting the whole story behind the design. So often what you see when you're looking at design documentation is a snapshot of the final design or the final product. This is what we did. And maybe you'll get a little bit about this is why we did it, but you're probably not going to get these are the things we thought about doing and didn't do and why we didn't choose those. And the problem is if you don't have that information, you run the risk of having things happen like with the ham, where somebody makes a decision under one set of circumstances, and then this can get carried through for years, even if circumstances change, and even if there might be better ways of doing things. To pull a software example, somebody could decide to build a project in a certain language. So when I was working on my master's degree in, this was in 1998, I decided I want to implement it in Java. Not because, I thought Java was the absolute best language for what I was doing, but because Java was still fairly new at the time and I wanted an excuse to learn it. And you actually see a lot of that on the job. People will often make decisions on doing things because they want an excuse to buy, an iPad, or to learn a new language, or to get a chance to go to some interesting place that they have to go to learn about the tool. So people make decisions for a lot of reasons, and it's useful to know what those reasons are so that when you're making a change further down the line, you're not risking breaking something. A classic example in rationale would be there was a bridge, a pedestrian walkway, and I believe it was in Paris, where somebody made a change in materials. So now we're getting into a mechanical or civil engineering domain, really, where they substituted out a material because they thought they chose a particular material for aesthetics, so because it looked nice. So they said, well, here's this other one that will, make it look even better. So they switched it out, but what they didn't realize was part of the reason behind the earlier decision was that there were key structural benefits also provided by this material. So swapping a material that had desirable structural properties for one that did not have those desirable structural properties resulted in a pedestrian walkway crashing to the ground. So this is generally not good. One of the things you want to be careful with your designs is that you don't want to design something that's going to hurt people. So just to give a little example of what rationale looks like, and this is a very simplified version, is here are some from a conference room scheduling system that I had worked with as sort of a research example. So one of the decisions you're making, I'm writing a software system where you can schedule meetings. And one of the decisions is, well, how do we represent our conference room in our system? There's a lot of different ways. One of the cool things with software is you can change it and do a lot of different things, so which means you have a lot of different options. So one is, well, I'm going to define the meeting as a class in the software, and I'm going to have a string that just gives the name of the conference room. So for every meeting, you give the name of the room that the meeting is in, and you store that in your system. And this is very simple to code up. You're just storing this name. But the problem with that is it's hard to extend it. So another alternative would be to create the conference room as the class. And those of you who are in 174 right now, you probably aren't going to start doing a lot with classes until the next semester. But the idea is you have a class that contains all the data about something. And if you have the conference room not just as the name of a conference room, but a class that can hold all of this other information about a conference room, then you can know useful things like, is there a projector? Often if I have meetings, I like to be able to bring my laptop and project slides during the meeting. Does it have a phone? If you want to do a teleconference, you kind of need a phone in the conference room. How many people fit in the conference room? We've got conference rooms that will hold 30 or 40 people comfortably, and we've got conference rooms that are going to be crowded with 10. So you can start keeping all of this information about the rooms if you go with a more complicated decision. So maybe in an initial version of the conference room system, you might say, I just want to have the names of the rooms. But you may think about later down the line, you may say, well, we need to extend it, and you want to go with a different solution. So the reason that rationale is useful is that this is kind of gives you the intent between the developer and the designer. So when somebody's designing some object, you know why they did it the way they did it. And it can help keep from duplicating things that have already been done. So if somebody already tried writing the software in a particular way, or they already studied using a particular material and then realized this is a bad idea, you're capturing that information, you're saving those reasons so that, you know, a year later somebody else doesn't say, gee, why don't we do it this other way? And then go through that analysis all over again. And it also lets you avoid repeating past mistakes. So if you did something and it failed, or your research said this is a bad idea, you don't want to go down that road again. You don't want to go down that road and not catch the thing that made it a problem. And this kind of preserves this idea of corporate knowledge. A lot of the knowledge that goes into building a product can get captured this way. But the thing is this isn't something that is typically used. Even though it seems like it would be real common sense to save it, it isn't done it. And this is because taking the time to record all of the reasons kind of slows you down. So you guys are already getting started on class projects, and you know, this idea of I need to get this done quickly never really goes away. It's kind of tedious to write all the stuff down. I know, because I've had to do it in my system, and you know, it's not one of the more fun parts about everybody's job. Nobody ever says, wow, the thing I like best about my job is writing documentation. You know, that just doesn't happen. The other thing too is if you tried like 5 things before something worked, you don't necessarily want to be confessing that to your boss. So you need to be in a climate where you can do that and it's okay. And then they're also, because not a lot of people are doing it, we don't have any data really showing, yes, it's really going to be worth the effort. And then also, there aren't really good systems to do that, and that's one of the areas that I'm trying to address in my research. So I've been looking at software maintenance in particular, because when you're working on a software project, these systems can take a long time to be developed, and they can live for a long time. I worked on one large radar system that while I was working on it, it celebrated its 30th anniversary. You know, and that was, at the time, more years than I'd been alive, and it was kind of amazing. And you know, there's some software buried in there that actually is 30 years old. So because the life cycle is so long, it's really expensive to have to go in and change a system that's been around that long. The chance of the person who wrote that code 30 years ago still being with the company is pretty tiny. You know, so you're probably not going to be able to get those people. So yeah, the obvious thing is, well, ask so-and-so why they did it. Well, they may not be around, and also people don't always remember. I mean, I often find I can't remember why I did something a certain way until I go back and look it up. So by having this information, this can help people, maintainers and designers of new products, be able to find problems and fix problems and be able to extend particularly software with less risk involved. So I want to talk a little bit about some of the current and future projects that I'm working on to kind of give you an idea of some of the things we're doing. So I have 4 that I'm going to concentrate on. So one is a project called Seurat, and those of you who are taking computer science classes are likely to. When I teach the software engineering course, which is one of the ones I teach, I'll usually have a lab where you'd be working with this tool. So this is software engineering using Rationale system. I have another project called the Rationale Creativity and Critical Thinking Project. And that's something that I'm also hoping to be able to do some stuff with in the classroom. I have a Rationale-enabled wiki system. And then I have a very large project that I was given $500,000 from the US government to try to extract rationale from existing documents. And one of the things I can do with that money, or a major thing I'm doing with that money, is to be funding graduate students. So I don't know if you're aware of this, but if you're a strong student, generally graduate school in computer science, and I suspect a lot of engineering as well, is free. I'll have students say, yeah, graduate school sounds great, but I can't pay for any more college. Well, I actually have money to fund 2 students this year, and was not able to get any in. We actually have a shortage. So, you know, we end up having a lot of students coming from overseas. We don't have enough students here. So if you're thinking, yeah, this research thing, that sounds kind of interesting, but I can't afford any more school, do well and you won't need to pay for it. So for the Seurat system is using Eclipse. So how many of you are using Eclipse or 174? I know some people are. So a couple of hands. So this actually plugs into Eclipse. So it runs as part of Eclipse. And Eclipse is a development environment that you use to write software in. And the idea is I want to use it to sort of look for possible errors in design decisions. So here's the system. So if you've seen Eclipse, this should look really, really familiar, because it's Eclipse with a couple of extra things added. So I've got a system that this shows all of the decisions, alternatives, and arguments. And this is all stored in a database. This is the Java Package Explorer. So if you're using Eclipse, you've seen this. And the way I augment it is I was able to add onto it a little icon to show if you have any rationale associated with a class. This is just the Eclipse source code editor. And you can edit code, and I use the Eclipse bookmark so that somebody editing will know if there's rationale there. And then I also have a task list that shows where there might be some problems. So this is a system that I started working on as part of my PhD work, which is at Worcester Polytechnic Institute. And I have now been continuing working on this since coming here. So for Seurat, I have worked with a lot of students. So the picture is I had a bunch of capstone students working with me a few years ago. And they were all adding various extensions into Seurat, which was absolutely terrific. And I got to go show off their marvelous work at a conference in Germany. I also had a graduate student who had been working on it with me. And then I have an undergraduate student, Yetchen, who did an undergraduate summer scholar program with me last summer, as well as a independent research. So a couple of ways to get involved in research, besides the ones you've already heard of, is we have a summer program called the Undergraduate Summer Scholars. And I recommend, if you're interested in doing this, I kind of like the idea of doing it between the sophomore and junior year, because you've had enough experience that you can really contribute something to research, but it still would leave that summer between your junior and senior year available if you want to do an internship. So this can be a good thing. It's competitive. Not everybody gets to do it. We were allowed, I think the computer science department was awarded 3 of them for the summer. And it pairs an undergraduate student with a faculty member to work on a project in the summer. And the other way to do it is you can do independent research, and generally that in computer science that counts as a technical elective. The way to get to do that is generally the faculty member needs to know you pretty well and to know that you're going to be able to do something useful. So again, this is something that you can talk to your professors about if it's something you think you might want to do. So the other project is the Rationale, Critical Thinking, and Creativity project. And in this one, so this is aimed at education. So one of the things with research that a lot of us try to do is integrate it in with education as much as possible. And of course, part of this is getting students to work with us on our research. Part of it is talking to our classes about new research developments that apply to the material we're teaching. But another way to do it is actually to do research more directly on education. So the question that I had was, I wondered if recording the rationale could help you guys come up with better, more creative design solutions. So what I was seeing in some of my classes was that I would have students who, when having to make a decision, were picking kind of the thing they were most comfortable with, or the thing they learned the most recently in the last class, maybe not reasoning through all of the different alternatives. And this can be really bad. I had a few people propose something where there was some way to do it that would have been just so much easier if they just thought a little bit more about what they could do. So what I'm working on here is it should be web-based, not we-based. So web-based version of Seurat that's designed for use in class projects. So I've had a undergraduate student, Tom Barber, working with me, and then also Shelby Wegren has just started. Is Tom here? Tom is not here. Okay, I was hoping Tom could come today, but he has been working with me on that project. He did a research independent, he worked for me the summer before last, then he did a research independent study with me, and then now I'm paying him out of one of my research grants to work with me. And he's got the Nestle Fellowship, which is another way of getting some money towards tuition. So we're hoping to do some experiments this spring. So some of you might be experimented on as part of this project. So and the idea is I want to be able to give sort of these rationale-based assignments to students at different levels. So I want to sort of get some freshman classes, sophomore, junior, senior on up, with different amounts of data already given to you to sort of analyze, can we get better solutions by using rationale? Would this be a useful educational tool? So you might be seeing this. Another project that we worked on last year is I did a rationale-enabled wiki. So again, I had Tom working on this one, as well as Annika and Derek. And this was over 2 semesters. And the idea here was we wanted to integrate rationale in with the Drupal content management system. So the idea was you would have your design documents that you were working on, and you could pull rationale out of them by just highlighting them, clicking a button, and having it put into the database. And then you could be able to structure it into a tree, looking a lot like the way Seurat did it. So again, the idea is to have the rationale, be able to pull rationale from stuff you're writing anyway, rather than having it be this extra step. And here's just a little screenshot of their project, which does not come out terribly readable, but you've sort of got some rationale over on the right, and then you've got a document on the left where some of the text has been highlighted and encoded as rationale. And then I've got the big project, and this is the rationale extraction from existing documents. And I have, the idea here is I'm using artificial intelligence techniques like machine learning and natural language processing to extract rationale from documents that already exist. And I'm looking at stuff from open source repositories because you can get a lot of data, but it's all very informal and unstructured. So is there a way to be able to, without human intervention or with very minimal human intervention, to go through these documents and automatically pull out what sentences in these might be rationale that can describe the decisions that were made as the code was modified. And I've had a couple of graduate students working with me on this, and I also have 2 undergraduate students, Yetchen and James, who are working with me on this starting this semester. So they're just getting going. So if you're interested in more about this, you can come see me, send me email. I have my website. I have pointers to my research pages. I have a book, but I'm sure you guys have enough reading to do in your classes. But the things I have going on. So I hear the textbook rustling, so I'm guessing I'm out of time. But does anybody have any questions? Yeah?
Have you ever thought of using game theory with your rationale?
The question is, have I ever thought about using game theory? And I actually have looked a little bit with that because there is some work, particularly in the evaluating which alternative might be best, because you are trying to kind of get an optimal solution. So I've looked at it. I haven't really done much with it. Any other questions? All right, well, thank you.